and welcome to today's webinar on improving crystallization and precipitation, a review of 20 years of best practice part 2. As you can see, this is actually part 2 in a webinar series that we're conducting on the topic of improving crystallization and precipitation. My name is Des O'Grady and I am a technology and application consultant specializing in crystallization and the use of the FBRM and PVM tools. So I'm just going to start with a quick overview of what we're going to go through today. We're going to start with a brief discussion on process and product quality. Then we'll move on to a crystallization workflow, a typical crystallization workflow, and then some industrial case studies that come out of that typical workflow. Throughout the course of the webinar, we're going to look at a number of different references available in the literature, and I'm going to give out a reference list. If you would like a copy of the reference list, please contact me at des.o'grady@mt.com or else contact your local technology and application consultant. So the question we ask, the title of this slide is, why is crystallization important? And I think it boils down to two key points. The first being product performance, the product quality of the crystals that you produce, and then secondly the process performance, in other words the quality of the process that generates these crystals. So I've taken a quote from a paper by Kim et al. From Bristol Myers Squibb, Control of Particle Properties of Drug Substance by Crystallization Engineering and the Effect on Drug Product Formulation. And I just took a couple of quotes from it. The first centered around product performance. Crystallization of an API in particular is critical for product qualities such as chemical purity and correct polymorphic form, which need to be strictly controlled to meet set specifications. So this is just a quick example from the literature showing the importance, or one aspect of the importance of product performance and product quality when you're running a crystallization. The second quote from the same paper centers around process performance. The quote goes, "The AIP crystallization process and crystal properties have a significant effect on downstream processing. For example, excess fines or wide particle size distribution may cause slow filtration and inefficient drying, which may be a major bottleneck of the entire manufacturing process." So ultimately, when we design, develop, scale up and optimize crystallization processes, the goal is to produce a product which performs well and which has the adequate quality, and then also allied with that is the need to produce a process which is going to behave efficiently as well. And I have an example of that on the next slide. So here's a PVM image from Crystallization A. This is just a cartoon or a kind of a very simple example of the idea of comparing product and process performance. So in Crystallization A, we can see immediately from the PVM image what type of crystallization we have. We can see we have large, kind of what look like agglomerates or maybe some amorphous crystals in our system, but also as well you can see there's a lot of fine material in there as well. So if you consider how a crystallization that produces a product such as this, how it's going to filter, you'd probably think it's not going to filter very well, because those small crystals are going to get caught in between the larger ones in the filter bed, and it's going to take a long time for the filtrate to wash through. So what you might do in this case is, you see you have a filtration problem, the PVM identifies what's causing the issue, so you might redesign the crystallization. And having redesigned the crystallization, you may come up with something that looks a little bit more like this. So here we can see we've produced in Crystallization B these very nice large boulder-like material, all of a similar size with no fine material. And chances are that this crystallization is going to filter, or this product is going to filter very quickly. The voids left in between, the gaps between those crystals, are going to be adequate for the filtrate to flow through, and it's going to filter quickly. Now what we haven't considered in this case, even though we've optimized our process, in other words, reduce the filtration time in this case, potentially what's happened is that we've negatively impacted the product quality. So for example, if crystallization A is the correct polymorphic form, we've changed our process parameters, now we're producing crystallization B, we can see it's a different morphology in this case, so maybe it's a different polymorphic form. So while we've improved the process, we may, in this case, have negatively impacted the product quality. And any crystallization design, you have to take both things into account. So you can't just improve the process at the expense of the product, or vice versa. So like I said on the bottom point here, on the bottom bullet, has there been a form or yield change resulting in undesirable product properties, even though we've improved the process? So a lot of the case studies we're going to look at today focus on how to improve product and process performance at the same time. So now we're going to look at a typical crystallization workflow, which I think is going to be familiar to a lot of people, and then some industrial case studies coming out of that. So this is a typical crystallization workflow that we've kind of generated based on our discussions with a lot of different people doing crystallization processes over the last few years. So if you just look at the top bar, when you get a new compound in, the first thing that you might try and do is just understand or develop process understanding. The next step might be to actually characterize. So in other words, see the impact of something like a cooling rate or an addition rate, changes to the cooling rate or the addition rate has on the crystallization. So maybe map out a kind of design space. Then you move on towards scale up when you move towards a kilo lab scale or perhaps even a pilot plant, and then finally on to production where you're going to manufacture large quantities of the material. And the scales that we work at typically when we do these steps we can see at the bottom. So you can see in the lab when you're understanding and characterizing, you might work between 5 mil and 5 litres. Between characterization and scale up, you might go from 5 litres in a kilo lab, for example, up to 100 litres in a pilot plant, and then on to production, which is generally more than 500 litres. So these are kind of arbitrary or average values of kind of what we see industrially. So some of the steps along the way that we typically see people working with, in the understanding stage, the solubility of metastable zone width determination is critical. This really maps out your design space and gives you information on theoretical yield as well as potential crystallization control strategies. And it's absolutely vital to get this information as early in development as possible. Next, you might move on to studying some polymorphic behavior. You want to try and lock down any polymorphic forms that occur as early in development as possible, so you're not caught by any surprises. Then you might move on to do some DOE studies during the characterization step to try and understand what process parameters impact, for example, the particle size. And then you might try and target a specific crystal size or particle size based on these studies. Seeding may become an issue as you move into the characterization step when you're really trying to look towards scaling up the process. And then as you move towards scale up, when you're actually producing material, maybe for clinical batches, being able to ensure formulability is very important also. As you move towards the actual scale up itself, when you go into the pilot plant, for example, the impact of mixing becomes important, and you have to consider how the mixing changes at the different scales, how that impacts both your process and your product. And then as you go towards production, the impact of impurities, for example, might be an issue. So let's say in a previous reaction step prior to the crystallization, maybe there's a varying impurity profile that's going to detrimentally impact your crystallization. It's important maybe to understand this. And then finally, process improvement. So really trying to improve product quality or the process quality itself. Now, in the previous webinar in this series, part 1 of the Improving Crystallization and Precipitation webinar series, we focused on a lot of these different aspects. So we focused on polymorphic behavior, we looked at ensuring formulability, we looked at the impact of impurities as well as a few other things. So if you're interested in any of these things that we don't talk about today, then by all means check out the webinar on demand, part 1 in this series. One of the things that we did look at in the previous webinar is the solubility of metastable zone width, and I'm actually just going to briefly repeat what we looked at there because it is extremely important. All the other case studies that we go through are going to be new, but this really is a critical case study. It's really the building blocks for your crystallization, so we're going to focus on this just for a moment. So the paper that we're taking this from is from Barrett and Glennon, characterizing the metastable zone width and solubility curve using FBRM and PVM from Chemical Engineering Research and Design. So in this study, FBRM was used to generate solubility and metastable zone width curves for a cooling crystallization. So if we look over on the right hand side, this figure 2 from the paper, we can see an FBRM trend over time. So on the x-axis is time. On the left-hand y-axis is the counts per second in 2 different size ranges. It's typical FBRM data. And then on the right-hand y-axis is the temperature in degrees C. So we can see that for the first 40 minutes of the experiment, the FBRM is measuring nothing, essentially. So it's a clear solution. But as the temperature is cooled, you can see that at around 50 degrees or so, there's a significant or dramatic increase in the number of particles or crystals that the FBRM is counting. So you can see that rapid increase there right around 50 minutes. And this corresponds to the point of nucleation, which is a point on the metastable zone width. So if we read up to the temperature at that point of increase, and we look across and see what the temperature was, we can see it was roughly around 25 degrees. Now, as soon as we see nucleation, we start to heat. So you can see now the temperature is increasing at about 60 minutes. And then over time, you can see that those counts actually drop off. And this happens because the crystals are disappearing. And we can see that around just before 80 minutes, you can see all the crystals have disappeared and the FBRM counts are back to 0. It's another clear solution. So that point of disappearance is actually a point on our solubility curve. That's the point at which they've all disappeared. And if we read up, we can see that occurs at roughly around 35 degrees. So 35 degrees is a point on our solubility curve. 25 degrees is a point on our metastable zone width for that concentration. So, like I said, FBRM accurately detected the point of nucleation and the point of dissolution, the metastable zone width and solubility point, respectively. And by measuring these points at different concentrations, so like I said, the figure 2 up there is for one single concentration, but by diluting, for example, you can change the concentration. We can generate a solubility curve and metastable zone width curve at a number of different concentrations. And that's exactly what they did in this case. So we can see we have solubility data here as the black circles. So we can see obviously at higher temperature we get more into solution. And then what they did was they actually measured the metastable zone width at 2 different cooling rates. So again, this is to gather information about the design space. And we can see that, as is typical with a lot of crystallization systems, the faster the cooling rate, the wider the metastable zone. And this is very important information when one considers scale-up, seeding protocol, targeting a specific particle size. Is information about the solubility and metastable zone width really defines your design space. And we can see that there's definitely an impact in the cooling rate that we choose, how far inside the metastable zone would we go. So some summary and conclusions. FBRM can be used to rapidly generate solubility and metastable zone width information. This can be automated. If you use, for example, something like an EasyMax or a LabMax, you can set it up to run overnight and you come back and you have this information generated for you immediately. So in effect, once it's set up, it doesn't take any work whatsoever. We're just quickly going to look at some PVM images, and they show different crystal morphology during the heating and cooling ramp. So you can see during the cooling step, 2 minutes after nucleation, we can see we have these octahedral crystals with these sharp points. Whereas during the dissolution process, we can see that those crystals have actually changed morphology and they're now much rounder. And the reason for that is the points of those octahedral crystals, the surface area to volume ratio is low, and we tend to get a lot of dissolution around that point. So the crystals actually change into a more spherical morphology. And this indicates that temperature cycling may be used to impact size and morphology of the crystals. When we heat up, we can see we change the morphology, and if we cool down in this case, maybe they're going to grow out as bigger spheres rather than reverting to that size or that morphology that we see. So temperature cycling shows that, or in this case, it shows that temperature cycling can potentially be used to impact size and morphology in this case. And the reason you might do this is to improve your process quality. So for example, it may filter or flow better if you have these more spherical crystals or rounder crystals. So our next example is DOE studies. And the paper we're going to look at is from Deneau and Steele at AstraZeneca, and it's an inline study of oiling out and crystallization. And like I said, all these references are here for you guys to check out, and the reference list will be available at the end. And if you want a copy of the list, please just get in touch with us. My email is des.o'grady@mt.com. So like I said, this is work done at AstraZeneca in Loughborough in the UK. So FBRM and PVM were used to understand and characterize a difficult crystallization process that exhibited phase separation, or more familiar to people, maybe oiling out. So we can see here a PVM image of an oiling out during the crystallization step. And essentially this usually happens when you cool or generate supersaturation too fast. We move into a different region of the phase diagram, and instead of crystals or a solid coming out of the liquid solution, we get an oil phase coming out of the solution. And we're going to look in a little bit more detail in another example of exactly what this is, and these references give a good idea about trying to understand exactly what oiling out is and phase separation, and perhaps how to avoid it. If we look below as well, we can see the FBRM trends. And I'm going to go through step by step what exactly is happening here, because I think just to look at this on this size screen may be a little bit difficult for some people. So what we see at first is a simple dissolution step. So we're heating up, and if we track the FBRM counts, much like we did in the solubility example, we can see they disappear. So we're just very simply tracking the dissolution step there. Then at a certain point, we see a rapid increase in the number of particles, or the number of counts that the FBRM sees. And when we compare this, or that time point, with the PVM images, we see that it's actually an oil phase that's crashing out. So we're actually characterizing with the FBRM that oiling out or phase separation, and we're confirming what it is with the PVM. So in other words, the PVM really helps us understand what's going on, and then the FBRM may give us kinetic information that can help us engineer the process around it. At the next point, we actually see coalescence of the oil droplets. And what happens here is the FBRM counts actually decrease. And if they showed, for example, a dimension statistic here, we probably see an increase in dimension of what the FBRM is counting. And the PVM images in the actual paper itself show those oil droplets getting bigger. The next step is actually we see the release of compound A from the droplets, and we actually get crystallization. So we see a couple of things here. First of all, we see the FBRM counts increase very rapidly, showing that we're getting the crystals coming out of solution. And then also the PVM shows the crystals coming out as well, if you look at the paper itself. And then finally, over time, they observe some crystal growth as the crystallization went on. So this oiling out occurrence is undesirable, because what it can lead to is purity issues. It can lead to sometimes unwanted agglomeration, which can impact the process. It can lead to scalability issues. This is something that you want to avoid on scale up, and also it leads to kind of a non-repeatable and non-robust crystallization. So what they did was they used a design of experiments to identify the process conditions that eliminated this phase separation, allowing for a scalable process to be designed. And going into more detail on the paper really shows the rationale behind this step. So a three-factor, three-level design of experiments protocol was constructed. And we can see what it looks like here. And what they varied was the seed size that they used, the seed loading or seed mass, and then the cooling rate as well. And if we just look at the DOE on the top right hand corner, table 1 there, we can see the size of seed on the low level was 20 to 45 microns. I think this was measured off a sieve. On the large level was 250 to 500 microns. The amount of seed was varied from 1 to 5 weight percent, so a small amount of seed and a large amount of seed. And then the cooling rate was varied between 0.1 and 0.5, and they had a midpoint for the cooling rate as well at 0.2 degrees C per minute. An FBRM was used in this case to identify and characterize the oiling out event for each set of conditions. So in this example that we see here on the bottom right, we're looking at 1% seed of 250 to 500 micron seed. So the 1% of the large seed at 3 different cooling rates. And what we can see on the FBRM data is, especially at the 0.3 degrees C, or sorry, the 0.5 degrees C per minute, is that there's that very large event where the counts increase rapidly, drop off, and then increase again. And what we're seeing here is the actual oiling out step. And you can see in all the cases that occurs. So you can see at 0.1 degrees C per minute, 0.2 degrees C per minute, there is that increase, then decrease, followed by an increase again, which is the crystals crashing out of solution. So what we can see here is definitely at the fast cooling rate at 0.3 degrees C per minute, the oiling out event is much worse. There's a lot more oil coming out of the system, whereas at 0.1 and 0.2 degrees C per minute, it's a lot less. Now if we look at a second example, we can see that at 5% seed loading, when they use the small seed, 20 to 45 microns, you can see that no oiling out was observed. Here in this case, what we see is just a rapid increase at the point at which the seed is added, and then the crystals grow out over time, or nucleate and grow out over time. And we can see that at all of the cooling rates that were used, no oiling out was observed. So basically this is very useful information, because as you scale up, the cooling rate that's available to you, or the consistency of the cooling rate, can vary quite a bit. So by being able to kind of eliminate this oiling out just by changing the seed loading and the seed size means that the cooling rate isn't going to be an issue as you move towards scale up. So like I said, the oiling out could be eliminated at all cooling rates investigated. This is their conclusion, for allowing for the crystallization to be further optimized and then scaled up. So now we're going to look at some seeding studies. This is from Leferrer, Hoff, and Wiesler. In situ monitoring of the impact of liquid-liquid phase separation on drug crystallization by seeding. And this is actually a similar example to the last one. This one's actually from Sanofi Aventis, but it kind of goes into, or takes a slightly different approach. So FBRM and PVM were used to study the impact of seeding protocol on crystal growth and nucleation, primary as well as secondary nucleation. So some of the results. The system investigated exhibited what they called LLPS, or liquid-liquid phase separation, what's sometimes also known as oiling out, under certain process conditions. So we can see here again some of the images that they saw with the PVM. The PVM is extremely valuable here because you can immediately see what you have inside your crystallization. You can see immediately that you don't have crystals, and in fact it's oil droplets. FBRM and turbidity were used to identify the phase separation boundary, in other words, the point at which this oil phase appears. PVM was then used to confirm the results by visualizing the droplets like we show in figure 6 in the top right there. And what we're looking at here on the bottom right is actually just the point at which they added seed in each case. So what we have here, this might look a little bit confusing to people, but it's simply a solubility curve. But in this case, the temperature is on the y-axis and the concentration is on the x-axis. Typically, when we see a solubility curve, it's the other way around. This was a very typical API system. There was two polymorphs, form 1 and form 2. You can see the blue and green lines there showing the solubility curve for each. And then the red line there is the liquid-liquid phase boundary. In other words, the point at which this phase separation was identified using the FBRM, the turbidity, and the PVM. So they used two seeding points in this example. So seeding point A, which was inside this liquid-liquid phase boundary, and then point C, which was outside or further over in the liquid-liquid phase boundary. So you'd expect when you see the point A, you wouldn't observe oiling out, but you would expect to see oiling out when you see the point C. So just like I said, two seed positions were used, A and seed, inside the metastable zone, and then inside what they deemed or termed this demiction zone. So let's look at some of the results that they got. So by seeding in the metastable zone, which is point A on the previous curve, FBRM identifies classical secondary nucleation and growth mechanisms after seeding. So we can see here on the FBRM trends that at the point at which they seed, the number of fine material, or the number of fine counts, increases after the seed, and this is typical of secondary nucleation. Whereas the number of large counts, you can see between 50 and 160 microns is the green curve, increases very steadily over time, and the number of actually smaller counts decrease as the crystals grow out of that smaller size range into the larger one. So this is classic secondary nucleation at the point of seeding, followed by crystal growth. And this is a very nice analysis because they've split up the FBRM data into two different size ranges to help with this understanding. Now the other thing that you see here is a comparison with turbidity, the blue line. And we see with the turbidity information doesn't really give you any information. So this is the comparison between the FBRM and the turbidity. The FBRM gives you information about secondary nucleation, crystal growth, whereas the turbidity really just tells you that you have particles there or you don't. So seeding inside this demixing zone results in a different process and product properties. And here we can see that the crystallization is now completely different just by changing the seeding position or the seeding temperature by a few degrees. So now we can see a very different mechanism at play. And again, we're going to take this in parts and look into it. So we can see the droplets and crystals form upon seeding. The droplets coalesce and the crystals grow. This is also confirmed by PVM, which is shown in the paper. We get secondary nucleation that occurs, and we can track that with the FBRM. You can see that increase in the fines. And then the droplets disappear. We see a slight drop in the fines, that's the droplets disappearing, and then the crystal growth and nucleation dominates over time. So we can see the different phases that the FBRM picks up, and we can identify and engineer around these. Again, the turbidity doesn't really give you that level of information at all. And one of the things that they pointed out in this example was the advantage of FBRM over turbidity is that particle population in different size classes as well as particle dimension can be monitored. So this is one of the reasons why they chose FBRM to really work with rather than turbidity in this case. So the next example we're going to look at is the impact of mixing. So this paper is from GlaxoSmithKline, Kougoulis-Jones, and Wood-Casimir, modeling particle disruption of an organic fine chemical compound using FBRM in agitated suspensions from Powder Technology. So in this example, FBRM was used to identify, track, and model crystal breakage and attrition in an agitated crystallizer for the purpose of predicting behavior on scale-up. So breakage is something that always concerns people when they go to scale-up, because it's very difficult to understand what changes in the mixing and what happens to change in the mixing and what impact that change is going to have on the crystals. So in other words, when you go to scale-up, are you going to get more or less breakage of the crystals, because that's going to change the result or the product as well as the process, subsequent downstream process that you get. So FBRM allowed changes in the crystal dimension and population to be monitored in situ and in real time. So if we look in this example, this is just one of the experiments that they did. This is an FBRM trend, and it's time in minutes on the x-axis, and we're looking at the relative number of particle counts, and we can see they increase over time like this. And what we're looking at here is in a specific size range between 0 and 10 microns. So what we're looking at here is over time the change in the number of fine crystals in the system. Now if we look, this is the exact same experiment, but what we're actually looking at here is just the change in a different size range. So this time between 100 and 300 microns. So it's the same experiment, and what we've seen is that over time there's an increase in the number of fines and a decrease in the number of large crystals. And what this is a classic example of is crystal breakage. So as the crystals break apart, the average crystal size gets smaller, we don't see as many big ones, and the number of fine crystals increases. So what they were able to track here and model was this breakage phenomenon and the breakage kinetics essentially. One thing that FBRM showed, and again if you goes into a little bit more detail in the paper, it showed that micro attrition rather than crystal breakage was the primary mechanism. So I suppose the difference here is that instead of the crystals breaking apart or breaking in half, it was really just the crystals were getting chipped away to produce these fine materials that we see on the top graph on the right hand side. A shift to smaller crystal dimension was observed as a specific power input was increased. In other words, an increase in the agitation intensity. So what they were able to do was to figure out what impact changes in the agitation intensity had on this breakage or attrition phenomenon. So here we can see the actual distributions from the FBRM. They did some modification to the actual chord length distributions from the FBRM, but the idea is still the same. So we can see the initial distribution is the solid black line, and we can see as the agitation intensity is changed, we see a decrease in dimension here, and we also see an increase in population. So we can see that depending on the agitation intensity used, we get a very different product out. So at high agitation we see a lot more fine material because the breakage rate is higher. So FBRM was successfully implemented to calculate attrition rates and produce a model for the disruption kernel of the organic compound. So we can see here, this is the model that they produce. So the specific power input on the x-axis, and then what they call deemed a net attrition generation rate, which I think is, if you go into the paper, it goes into more detail, but essentially a breakage rate. And we can see as the specific power input increases, that breakage rate increases as well, and they were able to model a pretty nice line there to show the relationship. Some of the quotes from the paper: FBRM offers distinct advantages over other measurement techniques as monitoring is performed in inline and in real time. So this was all done very quickly in a few experiments without any need for sampling. Very simple to do. And the importance of modeling particle attrition and disruption is such that it can be taken into account for the accurate prediction of crystallization behavior on scale-up. So this is obviously something that was important to them with regards to their scale-up strategy, was to be able to predict exactly what happens to this breakage rate or this net attrition generation rate on scale-up. So our final example before we go is process improvement. And this is from Sepracor Inc. And the authors are Musso, Saranteas, and Pritko. And the title of this paper was Crystallization Improvements of the Diastereomeric Kinetic Resolution Through Understanding of Secondary Nucleation. So in this study, the crystallization of a diastereomeric kinetic resolution was studied as part of a continuous process improvement initiative. So for those of you who might not be too familiar with diastereomeric crystallizations, in this case it's simply a case where you've got two enantiomers and you have to separate them out to produce the desired enantiomer. And typically the way that you do this is to use a resolving agent. So a resolving agent, it's typically like a high purity acid, for example. You mix it together with your solvent, your product, which is a mixture of the two enantiomers. There's a reaction, and that essentially changes the solubility of the enantiomers, enabling you to proceed through a standard crystallization step. So you can see here we mix our resolving agent, the product, the solvent together. We mix in heat, there's a reaction. Then we have our cooling crystallization where we add more solvent and seed. And then once we produce the desired enantiomer, we filter, wash, and then move on to drying where we have our product. In this case, the isolated intermediate was occasionally failing optical purity specs, and it also exhibited longer filtration and drying times. So we've kind of gone full circle here somewhat, and we've kind of gone back to the start in that we're looking now at an example where process as well as product quality is important. And in this case, they were able to fix both of the problems at the same time. So what they observed was that significant secondary nucleation occurred during the crystallization, and the temperature at which this occurred, Tn, or the secondary nucleation temperature Tn, this was identified as the critical response variable. What I think they did, they put together a very nice graph here, and what we're looking at here is the response of the process cycle time and the process purity, the diastereomeric excess, in other words, the optical purity of the compound, and how that relates to the secondary nucleation temperature. So we can see that at high secondary nucleation temperature, at high Tn around 45 degrees, you can see that the diastereomeric excess is very high, the optical purity is high, where and also, as well as that, the process cycle time is low at around 50 hours. Whereas at low Tn of 15, for example, you can see that the diastereomeric excess is very low, the optical purity is bad, and also the process cycle time is up around 100 hours as well. So clearly this response variable Tn is a critical one. So what they used was FBRM in this case to systematically estimate Tn at the lab scale, and then they moved towards a scale-up strategy to try and implement the changes that they made in the plant. So 1 litre experiments identified shear rate at the impeller tip and seed loading as the critical variables that influence TN, and obviously the TN subsequently influenced optical purity and filterability. So if we look here at some FBRM trends, in this case, we can see on the x-axis is time, and what we're looking at here is FBRM trends as well as temperature. So we've got 2 experiments side by side that we're comparing, and the first is low agitation and low seed loading. So what we can see here in this case is that the crystallization takes a long time to nucleate, and we can see the temperature at which it actually nucleates is low, and you can see it's actually around 12 degrees in this case. So we kind of highlighted that here. So for experiment 2, the TN is actually around 18 degrees. The enantiomeric excess is 85.7%, so that's a bad optical purity spec, and the filtration time in the lab was 150 seconds. The second experiment that they did was high agitation and seed loading. And in this case here, we can see the cooling rate is the same, but in this case, crystallization occurred much sooner. And if we highlight the results from this experiment, we can see the point on the FBRM around 100 minutes there where crystallization occurs. We can see TN in this case is high at 43.5 degrees C. The enantiomeric excess was 99.1%, so very good purity, and the filtration time was significantly quicker, 30 seconds in this case, which was 20% of the old value. So clearly what they've shown here at the lab scale is the importance of seeding and agitation to control this secondary nucleation event, and that subsequently controls the product and process quality. So implementing these changes, they obviously did a lot of work in between. I think they did, in the paper it mentions work that they did at 2 intermediate scales before they went up to full scale, but it reduced the centrifugation time by 66%. It eliminated the need for manual filter discharge. So what was happening in the initial case was that in some cases the filter would be so badly clogged and blocked that it would take an operator to go in and actually unclog or discharge the filter. And they reduced the number of fail batches from 3 out of 18 to 0 out of 39 in the campaign that they run. So obviously a very significant success. So I've just shown the summary of results, table 3 from the paper, that kind of summarizes this. So the secondary nucleation induction temperature in the original set of experiments was at 37 degrees. And the range, and perhaps this is even more important, is that the range was anywhere between 26 and 43 degrees C. So not only was this process in some cases bad, but it was impossible to predict how bad the process was going to be, how long was it going to take to filter, and that messes things up, like scheduling for subsequent filtration steps, or when you're going to be able to start a new batch, for example. But then when they implemented this new seeding protocol, 10x seeding, the average secondary nucleation temperature was 44 degrees, and the range was between 42 and 45 degrees, so a much tighter range. The centrifugation time was 7.5 hours in the original on average, and again this range was very large, between 3 and 12 hours, whereas the new experiment, the average was 2.2 hours, and the range was between 1 and 4. Again, they eliminated the need to manually discharge the filter, and then also the number of failed batches was reduced from 3 out of 18 to 0, essentially. So a very significant return on investment here through the hard work that they did engineering this problem, and also for the investment that they made in the technology. This is actually a really nice paper. There's some very good engineering work done in this paper that I haven't obviously got time to go into, but I'd very highly recommend that people go and read it, people who are involved in tech ops or process improvement. It's a very nice paper. So that completes the case studies that we're going to look at. What I will do is just show the references that are available. Firstly, I'd just like to thank the MT crystallization team for all their help. Paul Barrett, Terry Redman, Jorg Werlicek, Brian O'Sullivan, and Jochen Scholl. Some of these names might be familiar to a lot of you guys. And then here are some of the references. So if you want, just grab these from the webinar, or else just send us an email, get in touch with us, and we'd be happy to send them out to you. My email is des.o'grady@mt.com. These references that I'm showing here are actually from academia. and these ones are the industrial references. The other thing that I'd recommend to do is to go to the other webinar, part 1 of this webinar series, where we focused on, it's the exact same format as this one, but we focused on different case studies than the ones we looked at today from some of these papers. But all the papers that we looked at today are listed here. So that concludes the webinar. Thank you for your time, and I hope you enjoyed it.